So we'll go ahead and get started with today's seminar. Today we have Nadir Jeevanjee from GFDL/Princeton, where he's a postdoc in their visiting scientist program, I think is what it's called. So he doesn't come to us from too far away. He's only been there for a few months now, so he's going to mostly talk about a lot of the work that he did as a physics PhD student at Berkeley Lab. With the Berkeley Lab and at the University of Berkeley. And before that, he did his undergrad in physics and mathematics from USC, and then started his master's at Berkeley in physics. And during this time, he spent some time traveling as in a rock band. And to make that even more unique, while he was traveling in a rock band, he actually wrote a textbook on tensors and group theory that now there's a second edition of, so that's very productive graduate student time. Maybe it was a graduate student longer than we would necessarily like graduate students to be. So with that, today he's going to talk about effective buoyancy and atmospheric convection.
All right, thanks a lot, Kevin. It's great to be here. And yes, my tenure as a grad student was extra long, so it did, I did have a lot of fun, and I did do a lot of different things. It took time. No regrets, so a little bit of an unusual trajectory. So today, yes, I'm going to talk about my PhD work, which really focused on trying to understand what are the forces that act on convecting air parcels. And so a specific question that we asked was, what triggers tropical convection? We know that that convection is buoyancy driven, but is that how convection gets its start? Are convecting parcels, do they really float up from the surface because they've been warmed by the surface? Or do they get sort of pushed up by air currents that are moving around? And we focused on tropical convection because that's where most of the rainfall is in the tropics. And this question of triggering, besides being interesting, an answer to this question would then inform convective parameterizations in global climate models. So it's not just an academic question. What we learn from this will hopefully actually get fed up into global models. All right, so one thing we do know about triggering in the tropics is that it often happens on the edges of cold pools. So what do I mean by that, and what are cold pools? So what you're seeing here in the satellite image are the remnants of deep convection. You see maybe 1, 2, 3, maybe 4 remnants of deep convective events. And so this kind of wispy stuff you see in the center is the dissipating anvil from a deep convective event, right? Deep convection rises up and then spreads out in an anvil cloud, and that takes time to dissipate. But another thing that happens is you get a rain shaft. Some of that rain evaporates near the bottom, and then kind of slumps down and spreads out into a cold pool. And what you can see here in these rings of incipient convection, that's actually marking the edge of the cold pool, and there's new convection being triggered on the edge. And you can see this very dramatically in this photo. So the first thing I want to do in this talk, and what I'll focus on in maybe this first 20 minutes, is to try and understand this triggering, what's happening. And the context in which we'll do this is a modeling context, and we're going to the type of model simulation we're going to look at is radiative-convective equilibrium. So I think you may have seen a few talks about such a system, but I'll just remind you what that is. So this is a movie of the type of simulation that I'll be using. So what are we looking at here? So this is just a box of atmosphere. The box is doubly periodic in the horizontal, so what comes out on the left just comes back in on the right. There's an ocean surface with a fixed constant temperature. And what you're seeing here is actually these colors represent the temperature of the near surface air, and I'll come back to that in a minute. But what's happening in this model is that the warm ocean surface is warming and moistening the boundary layer, the air near the surface. The atmosphere is also coupled to a radiation scheme that provides infrared radiative cooling throughout the bulk of the atmosphere. And what this convection is doing as it's rising up is it's really taking moisture from near the surface, raising it up. That moisture condenses, releases its latent heat. And this convection is vertically distributing that latent heat in the vertical to compensate for the radiative cooling. And so that's why we call this radiative-convective equilibrium. And if I just pause this, then let's see here. Let me go back to the beginning. Oops. Well, and so what you see here are some cold pools of air. So you see the remnants of the convection up here. The evaporated rain has produced a cold pool, and you can see some triggering of new convection on the edge. So this looks qualitatively similar to what we saw in that satellite photo. All right. So to get a better look at this triggering, now we're going to take a similar simulation, and we're going to look at an XY view of certain quantities at low levels. So here's the Archimedean buoyancy. Here's Archimedes right here, to remind you. And this is plotted at the lowest model level. These are the x and y axes. And so you see here a giant cold pool and maybe a couple smaller ones made visible by their negative Archimedean buoyancies. And here's the vertical velocity at 300 meters, kind of in the middle of the boundary layer. And indeed, you see that the vertical velocity plot really lights up at the edge of the cold pool, right? Again, consistent with that satellite image. And so the question we want to ask is, what's causing this? What are the forces that are at play? Why does this happen? And so the thinking for a long time was that as this cold pool is spreading out, you get horizontal convergence at its boundaries, at the edges. And indeed, if I plot the horizontal convergence, it also lights up at the edges of the cold pool. So that seems pretty plausible. You know, it's a sort of plausible mechanism, and these plots are obviously tightly correlated. But then one thing that Adrian Tompkins showed about 15 years ago is that if you look at thermodynamic quantities, such as the equivalent potential temperature, theta E, and the equivalent potential temperature, very roughly, is the temperature the air would have if you converted all the latent heat of water vapor into sensible heat of the parcel. So it's measuring not just the actual temperature, but also the contribution from water vapor. And you see that this also lights up around the edges of the cold pool. And so this suggests that there's maybe a thermodynamic component to the triggering and the initiation of convection. And so that's the question we want to answer is, which of these effects dominate? You know, is this triggering thermodynamic in nature, or is it kind of mechanical in nature? Well, in order to compare these guys, I can't really compare potential temperature and horizontal convergence. They don't even have the same units, right? So I somehow need to convert these into forces, which I can then compare. So for the thermodynamic force, we're going to call that force the effective buoyancy. And I'm going to define it very simply. It's just going to be the vertical acceleration a particle would experience if you zeroed out all the wind fields, so that there's no mechanical forcing of any kind. And if I take this definition and apply it to the equations of motion, I get this equation for it. And it's a Poisson equation, so it's saying that the Laplacian of the effective buoyancy is given by this source term. This looks a little complicated. There's like several derivatives here. This h mean, the subscript h means only take the horizontal parts of the Laplacian, so a delta x squared plus a delta y squared, but no delta z squared. And here we have the hydrostatic pressure. So what does this equation mean, and why is vertical acceleration sourced by horizontal gradients of hydrostatic pressure? So this equation looks kind of opaque, but my claim is that all it's saying is that you can think of clouds as being driven in the same way that chimneys act. So if you look up on Wikipedia how a chimney works, you'll see that you'll get this image. And this is just saying that if you have a column of warm air, then that column is lighter than the environment, so its hydrostatic pressure is lower. So there's a hydrostatic pressure gradient driving air, converging air inwards, right? But we know that air is not really allowed to pile up in any one place in the atmosphere, right? The Earth's atmosphere is approximately incompressible. And so if you've got convergence in the horizontal here, you must have divergence in the vertical. And so that forces some vertical motion. And so to apply this to a convecting air parcel, so let's say I've got a density anomaly here and therefore a hydrostatic pressure anomaly here. And that hydrostatic pressure anomaly will also extend below the parcel, right? So if there's a hydrostatic pressure anomaly, then I'll have a hydrostatic pressure gradient converging mass inwards. But mass is not allowed to pile up. So there must be a compensating pressure force which cancels out this convergence, right? So we'll call this pressure the buoyancy pressure. And this is how it's going to act. It's going to push outwards, and it's also going to push up. And this equation is just saying that the divergence that's coming from the gradient of the buoyancy pressure exactly cancels, that's where the minus sign comes from, the convergence from the hydrostatic pressure gradient, right? So the job of this guy is just to cancel out the divergence from the blue arrows. And my claim, so this is just just the same picture as I painted for the chimney. And my claim is that the effective buoyancy is actually just the vertical gradient of this pressure field. And in fact, if you just take d dz of both sides of this equation, then you get this equation that I showed you before. So the equation looks complicated, but it actually is painting a very simple picture. Right? All right, so that's the thermodynamic force. What about the mechanical force? Well, we're going to call it the inertial acceleration, for reasons that I'll make clear in a second. And again, we're going to give it a simple definition. It's just going to be the vertical acceleration a parcel would experience if you zeroed out any horizontal density anomalies. So rho bar here is a horizontally average density. And so this is just, so if you set rho equal rho bar, then you've got no density anomalies. You've got no buoyancy, basically. And so whatever's left should be the mechanical forcing. So again, you can plug this into the equations of motion and derive a Poisson equation for this. But here, the source is the advection term in the momentum equation. But advection of momentum is just another name for inertia, right? So that's why we call it the inertial acceleration. And similar to this, so you can think of this equation as saying as the effective buoyancy just compensates for mass convergence from hydrostatic pressure gradients. Similarly, the inertial force is just compensating for convergence due to advection of momentum. That's how you can think about it. All right, and it's a mathematical fact that this gives a complete accounting of the vertical forces on a parcel. So this gives a nice decomposition of vertical force into a thermodynamic component and a mechanical component. All right, so now that we've done that work, we can just take these expressions for these forces, solve the Poisson equations numerically, given the model output, and just diagnose these forces and plot them. And this is what you get. All the accelerations, these three accelerations are all plotted on the same color bar, so there's nothing funny happening there. And so you see very clearly that it looks like the inertial force is dominating, right? It's several times larger than the effective buoyancy, and it's co-located with the vertical velocities. And one thing to note here is that the Archimedean buoyancy looks completely different from the effective buoyancy, just wildly different, right? So in this case, the Archimedean buoyancy is an extremely poor indicator of thermodynamic accelerations. And the second half of my talk is going to focus on the discrepancy and try to understand what's wrong with the Archimedean formulation, or what's incomplete about it. All right, so this is kind of strong eyeball evidence that it's really the mechanical forcing, the inertial acceleration that's dominating. But we'd like to do a little bit better than just eyeball evidence. So we'll do something a little bit more objective and comprehensive, and we'll just do some simple regressions. So what I'm going to do is I'm going to do two separate regressions. I'm going to regress the inertial force at some height z below 300 meters against the vertical velocity squared at 300 meters. And the reason I'm using vertical velocity squared is because the work energy theorem says that forces should be proportional to velocities squared. And I'm regressing the force on the velocity, not the other way around, because I want the regression coefficient to be proportional to the influence of the force. And I restrict myself to grid cells that surpass some threshold of velocity. So here's the result. So I'm applying the regression coefficient on the vertical axis. The height at which the force is evaluated, this z, is plotted on the horizontal. And again, you see that the inertial force is dominating by a factor of maybe 5 or 10 or something like that. All right. So we seem to have a pretty unequivocal answer as to which force is dominating. It's the inertial acceleration, the mechanical force that's dominating. But why? Why doesn't buoyancy play a role? So what I've got here is a cartoon, and this is sort of a cross-section where this is the radial direction, and this is z. And here's the sort of you can think of this as the downdraft that generates the cold pool. So this is a cylinder of air moving downward because it's negatively buoyant with some buoyancy b. And that negative buoyancy, again, comes from evaporation of rain. And then there's slumping out and spreading out radially with some velocity u. The downdraft has height capital H. And the gust front here, the edge of the cold pool, has a height lowercase h. And what I want to do is I want to evaluate the ratio of these forces here, where the triggering happens. Well, so if I just look at those Poisson equations, I can make an estimate, and I get that this ratio should go as u squared, because this guy is sourced by the advection term in the momentum equation, which has 2 factors of u. And the effective buoyancy is sourced by hydrostatic pressure gradients. But the hydrostatic pressure differential across the gust frontier is basically proportional to the buoyancy times lowercase h, right? All right. But the kinetic energy of this gust front is derived from the gravitational potential energy of the downdraft. So this u should actually scale as square root of bh, and that's capital H here. So when I plug that in here, I just get this simple dimensionless ratio of the downdraft height to the gust front height, which again, maybe it's a factor of 5 or 10, comparable to the ratio of these forces that we saw in the last couple plots. So that gives a sort of kind of basic physical understanding of why the inertial force dominates, and it gives it to you in terms of a dimensionless ratio of just geometric quantities. All right. So we wanted to understand a little bit more about what triggers tropical convection, and we found that indeed, as people had thought for a while, it is the mechanical forcing. And these results are written up in a 2015 JAZZ paper, and then my advisor David Romps followed up with an analytical theory for the sizes and lifetimes of cold pools, which I helped him test with numerical simulations, and that was published earlier this year. But there's still unanswered questions, right? Such as, how can these two quantities just be so different? How can the Archimedean buoyancy lead us so astray, at least in this context? And so the second part of this talk is going to be to try and to understand and hopefully to quantify this relationship between the effective buoyancy and the Archimedean buoyancy. And since we're shifting gears here, maybe it's a good time to pause and take questions on this first part, if there are any.
When you did the regression,
yes.
the vertical velocity is squared.
Yes.
So you left out the small velocity, right?
That's correct. I only wanted to sample places where it looked like convection was actually being triggered.
But isn't the initiation of convection begins with small velocity? So you are missing out the initiation process.
So I guess what I was doing is I was looking for...
So actually the question I'm asking is that since maybe you have done it now, so does the regression look very different, or does the relationship look very different, or velocity is near zero? That's what I'm asking.
Well, I mean, I think I'm sure the regression would look different. But I think what so I'm looking at the vertical velocity at 300 meters and trying to regress it on the forces at, say, 100 or 150 meters, right? Now, at 5 meters per second, it only takes maybe, I don't know, a handful of minutes or less even, to travel that far, right? And so the thermodynamic fields aren't really evolving very much in that time. So if I just take one snapshot and I look at the vertical velocities here, because not that much time has elapsed since that parcel was down here where those forces were acting on it, right? I can pretty much regard the force fields here as the forces that were acting on this parcel. So what I'm saying is, okay, I want to look at parcels that I know have been initiated, which is why I put in that velocity threshold, so that I'm only looking at particles that are already starting to convect. And then I ask, what were the forces that acted on that parcel? And in particular, was the inertial force greater than the effective buoyancy? Does that answer your question?
I understand the argument, but this is an ipso facto. I mean, it already assumes an understanding of the process.
No, it's assuming that. I mean, it assumes that the convection here was generated by some forces, and the question I'm trying to answer is which force.
Okay, so we will discuss it.
Okay.
So your effective buoyancy is basically just you include pressure gradient.
Yeah, so another way to think about it is it's the Archimedean buoyancy plus the perturbation pressure gradient due to buoyancy. So yes, there's another way of formulating the equations where you have the effective buoyancy is equal to the buoyancy term plus this perturbation pressure gradient, for which you also have to solve the Poisson equation. That's right. Other questions? Yeah.
those two terms, that by chance, the other one is larger? I mean, by the cases you analyze, for some more samples cases, is there any cases to support that buoyancy will be more important? It's just
Sure. I mean, if you don't have cold pools, right? I mean, if this whole argument is well, the cartoon picture that I painted to understand this argument is in terms of a cold pool. So if you have, say, non-precipitating convection or only lightly precipitating convection, right, then you actually might not expect the mechanical forcing to dominate. And in fact, I have a backup slide. I mean, maybe I'll just show you now. So what I did here is I did simulations that transition from shallow to deep convection. And so in the beginning, there's no precipitation. And you see that the effective buoyancy regression coefficient is larger. And as the precipitation ramps up, so does the influence of the inertial forcing. All right.
Yeah, just back to that case again. So it seems that even for that case, initially they are, even with no cold pool, the mechanical forcing is still close to the buoyancy forcing, at least the regression.
Oh, you mean for the case I just showed?
Yeah,
in the
for
shallow
case that you
precipitation?
just showed.
Uh-huh.
So how do you interpret that mechanical forcing? So
Oh, I see. If there's no cold pools?
yeah.
That's a good question. I'm speculating here because I haven't looked into it. But there are dynamic pressure fields, so we do know that if you start to have convection, and let's say it's buoyancy driven, right? Then both air below that convecting parcel and air above is all accelerated vertically upward. And in part to what's usually, well, and it's essentially due to inertia, to advection of momentum. And so that would show up in the inertial acceleration. So that would be the, this air is buoyant, this air is not, but this air is moving up, and so this air kind of gets sucked up behind it. And so the force that's acting on this guy would appear as an inertial acceleration. So that may be one thing that contributes to it.
Actually, environment should compensate because there is no net buoyancy.
Sorry?
Environment in that case should compensate with downdrafts, with negatively buoyant downdrafts.
Yes, you get those on the sides.
Yeah, because there is no net buoyancy.
Yeah, right. But you'll still have air directly underneath pulled up.
And that's what actually what makes you still that term. Even without all this negative buoyancy with the vector of light. You don't have pulse,
Uh-huh.
but you still have negative buoyancy around updraft.
Yeah, just the substance. That's right. All right. All right, so now we want to turn and focus on effective buoyancy and understand its relationship to the Archimedean buoyancy. So the way we're going to, and just as a preview, to kind of set the stage, what I did was I just took some Gaussian density anomalies that are sort of spherical, but with a Gaussian density distribution in R and in Z. And I numerically computed the Archimedean buoyancy and the effective buoyancy. And what it's plotted here are just X and Z cross-sections through the center of the bubble. And so again, these are plotted on the same color scale. And so you see that already the effective buoyancy is a factor of 2 smaller than the Archimedean buoyancy, just for this kind of standard bubble, right? And then what's interesting is that if I start to bring this bubble down towards the surface, the effective buoyancy decreases even more dramatically, right? I'm not changing the density anomaly, and the Archimedean buoyancy is just a function of the density anomaly, so that distribution doesn't change, but the effective buoyancy changes dramatically. So it seems like there's some role for the surface here. So what we're going to do then is we're going to take a sort of spherical cow approach and just do the simplest thing possible. I guess in this case it's more of a cylindrical cow. And so I just take some idealized cylinders with a uniform Archimedean buoyancy, some diameter d, some height h, and I consider a free cylinder that's just floating up somewhere high, far from any surface. And I consider a cylinder right at the surface where there's a beta equals 0 boundary condition. And what I'm going to do is I'm just going to borrow some methods from physics and use a method of Green's functions to analytically solve this equation and find the effective buoyancy at the center of the cylinder. So this is what we get for the free cylinder. So the effective buoyancy is just a function of the Archimedean buoyancy and the aspect ratio of the cylinder. And so you see that for small aspect ratio, so small aspect ratio means skinny and tall, right? So for these kinds of parcels, the effective buoyancy and the Archimedean buoyancy are basically the same. This ratio approaches, I'm plotting here, beta over B0. So their ratio approaches 1, right? And maybe that's what you expect. But then as the aspect ratio grows larger, the effective buoyancy starts to decline. And even at an aspect ratio of 2, you're really only at 50% of the Archimedean buoyancy. And that's actually just what we saw with those Gaussian bubbles a couple slides ago, which did have aspect ratio of 2. And you can play the same game for the surface. You get a slightly more complicated expression. And that's plotted in the dashed line. And qualitatively, it's similar. The ratio of effective to Archimedean buoyancies approaches 1, small aspect ratio, and decreases. But this decrease is much more marked, right? It's much more dramatic. OK, well, that's nice. So we have some simple analytical formula that quantify the relationship between the effective buoyancy and the Archimedean buoyancy. But we want to understand these formula, right? Why is there an aspect ratio dependence? And why does the surface so strongly inhibit the effective buoyancy? So the answer to the first question is that wider parcels have taller circulations. Well, what does that mean? So what I'm plotting here in both panels is the buoyancy pressure normalized by the hydrostatic pressure anomaly in the center of the cylinder. And so those are the contours. And what I'm plotting here is, again, an XZ cross-section through the cylinder. Both X and Z are normalized by the height of the cylinder. And I've done this for 2 cylinders of 2 different aspect ratios. And these pink squares are just cross-sections of the cylinders themselves, right? And the first thing to notice is that this ratio is equal to 1 for both cylinders. So the buoyancy pressure, the normalized buoyancy pressure, is the same in both cases. So that's not what's causing the difference. But you can see that the vertical scale over which the buoyancy pressure declines is much greater in this case than in this case. And what's happening is that when you have a really wide parcel, right, that width sets the length scale of the problem. And so then the buoyancy pressure must decline over that length scale. But then you're moving a taller column of air, but with the same pressure differential as in the skinnier case. And so, of course, the gradient has to go down, right? Fixed pressure differential, larger length scale, gradient goes down. So that's why the effective buoyancy is lower for larger aspect ratios. And the second question was, why does the surface inhibit effective buoyancy? And the answer is that it's symmetry breaking. So what does that mean? So this is the cartoon picture we had for the free cylinder, right? You have convergence from the hydrostatic pressure gradient, and then the buoyancy pressure responds by both pushing out and pushing up. But in this case, there's a symmetry. You actually have reflection symmetry about the z equals 0 axis, right? You can just see that in the differential equation. So that means that beta at cylinder top, this green arrow, has to actually be the exact same as beta at cylinder bottom. So that means there's actually no net vertical divergence into or out of the cylinder. And so if I'm going to balance the convergence from the blue arrows, I have to balance that entirely with the horizontal green arrows. So that means that the horizontal gradients of these 2 pressures are the same. And if you integrate that relationship up, you find that the 2 pressures have to be the same in the center of the cylinder. And that means that the ratio of these 2 guys would be 1, which is exactly what we saw on the contour plots a few slides ago, right? So let's contrast this with what happens when the cylinder is sitting at the surface. So now you still have convergence from the hydrostatic pressure. But now, beta is 0 at the bottom, and it's non-zero at the top. So now I do have some non-zero vertical divergence. So since I have some divergence in the vertical, these horizontal green arrows don't have to be as large. They don't have to exactly offset the horizontal blue arrows. So my horizontal gradient in PB is smaller than my horizontal gradient in the hydrostatic pressure. And when I integrate that up, I find that the buoyancy pressure is smaller than the hydrostatic pressure anomaly in this case. And that's the basic difference between the surface and free parcels. And the reason that happens is because this surface breaks the symmetry around the center of the cylinder that existed in this case. All right, so now if we return to our cold pools, then now it's maybe not too hard to understand why these two plots look so different, right? A cold pool has a very large aspect ratio, greater than 10 probably, and a cold pool sitting right at the surface. And so if I look at this plot, the ratio of effective buoyancy to Archimedean buoyancy, well, you're going to be on this dashed curve because you're at the surface, and you're going to be way out here at an aspect ratio of 10. So it's no wonder that the effective buoyancy basically looks, you basically get no signal from this cold pool. It's essentially 0. All right. So we wanted to understand and quantify the relationship between effective and Archimedean buoyancies. And we found some analytical formula which quantify it. And then we sort of constructed some cartoons to understand why these analytical formula behave the way they do. And these results were published earlier this year in QGRMS. And so now I want to turn to some applications. What can we do with all this? Well, so the first application is just to ask, do these formula work for non-idealized parcels? Right? I was considering these uniform cylinders. They couldn't be more idealized, but real convecting parcels are messy. Their buoyancy distributions are non-uniform. So do these simple idealized formula apply? So as a first step in that direction, let's just consider these Gaussian bubbles that I showed you. Right? So they have non-uniform buoyancies and non-uniform effective buoyancies. So what I'm going to do is I'm going to consider two sets of these bubbles, one set of free bubbles and one set of surface bubbles. And for each bubble, I'm going to average the effective buoyancies and separately average the Archimedean buoyancy over the volume, and then take their ratio. And I'm going to do this for several different aspect ratios. And I'm going to do this all numerically, right? So I solve the Poisson equation for beta numerically, divided by the average Archimedean buoyancy, and this is what I get. So this is all numerics. But against this, I can plot those analytical formulas that I had. And that's what they look like. And so it's not perfect, but it does a pretty good job. And so that's saying that even for these somewhat more realistic parcels, these idealized analytical formula are kind of capturing their essence, even if they're not perfectly exact. So maybe these formula are useful in that way. All right, so since you might reasonably apply this formula to realistic clouds, then maybe you can apply it to parametrizations of convection, such as are used in global climate models. So some global climate models actually parameterize the vertical velocity equation. When they have a convective parameterization that's mimicking the effects of convection, they actually have convective plumes that have a vertical velocity that evolves. And they often use an equation like this, which says that the vertical acceleration is given by a buoyancy term multiplied by a virtual mass coefficient. And then this is a drag term, right, meant to encompass both form drag as well as maybe mixing drag. And so this form is used often in the literature, but then a survey of the literature done by Deruta in 2012 shows that there's quite a lot of spread in the coefficients that people use. So here's the coefficients that people use for A. You see that most of them are less than 1, but not all of them. This one is 2. And there's quite a bit of spread in these values. And they're more or less ad hoc. But now, if we just take our definition of effective buoyancy as the acceleration you get when you zero out the velocity, well, then zeroing out the velocity means zeroing out this W. And so that tells you that, so if beta is the left-hand side, this gets zeroed out, and all you have is AB, then this virtual mass coefficient is really just this ratio of effective buoyancy to Archimedean buoyancy that we've been talking about, and which we have analytical formula for. So that means that if you have some convection scheme and you have some way of estimating the aspect ratio of your parcels, then you can make kind of a principled estimate of this coefficient rather than having to resort to the ad hoc values that are appearing in the literature and that have this large spread. All right, another application would be to kind of mapping out the hydrostatic gray zone. What do I mean by that? So the main result is that if you have some cylindrical parcel of these dimensions, then its effective buoyancy is given by this curve, as a function of its aspect ratio. But I can just re-envision the cylinder as, say, a GCM grid cell, right? And so now this plot is telling you how vertical accelerations, and hence vertical velocities, should change as a function of resolution. And so if you're running a typical global climate model, then maybe your resolution is 100 kilometers. Maybe your vertical grid spacing or the height of your convecting elements is 500 meters or 1 kilometer. So you're at an aspect ratio of 100, right? So you're way out in the next room, right? And so that's the hydrostatic limit. Your vertical accelerations are tiny, and they're so small you actually neglect them in the vertical momentum equation. That's the hydrostatic approximation, right? But as probably most of you know, computer power is increasing, model resolution is increasing, so we're starting to creep up this curve, right? And so now you're starting to get some explicit vertical motion. But it's often unclear, how much vertical motion are you getting compared to a sort of fully resolved simulation? And can you trust the amount of vertical motion that you're getting? And so maybe what these curves can do is kind of provide a map or a guide as to where you are. When you run a model at, say, 4 kilometers, which is often considered convection permitting, right? Well, if you're running a 4-kilometer simulation, and let's say you have a plume in the boundary layer, and the boundary layer is 1 kilometer deep, right? And you're at the surface, then your aspect ratio is 4, and you're going to be on this lower curve. And so your vertical acceleration is going to be 1/10 of the Archimedean value. And that may be fine for the purposes of your simulation, but it might be helpful to be able to ballpark that ahead of time and just know what kind of vertical accelerations do you expect to see for a given resolution. All right, finally, and this turns to some work that I'm doing now at GFDL. Another thing you can apply this to is to the overestimation of vertical acceleration in a hydrostatic system. Now that kind of sounds counterintuitive. I mean, hydrostatic systems, by definition, employ the hydrostatic approximation. And the hydrostatic approximation, the accelerations are so low that you neglect them from the vertical momentum equation. So how can a system simultaneously neglect a quantity but also overestimate it? Well, that's actually exactly what these systems do. So to understand this, let's go back to the non-hydrostatic case, the case that we've been discussing all along. I have my density anomaly. I have a hydrostatic pressure gradient. The buoyancy pressure responds and generates vertical acceleration. And the point I want to make here is that from the point of view of mass continuity, this vertical arrow only has to compensate for the net convergence here, right? There's convergence from the blue arrow, but some of that is offset by the green arrows. And so you have a smaller net convergence, and this vertical arrow has to compensate for that net convergence. But now let's say you're hydrostatic. And in a hydrostatic model, you set all your non-hydrostatic pressures, like the buoyancy pressure, to 0. So you still got hydrostatic pressure, so you still have hydrostatic pressure gradients converging mass into this volume. And mass continuity still has to be obeyed, so there still must be some vertical motion, right? And that's, in fact, exactly how a hydrostatic model diagnoses vertical velocity. It says, oh, I'm going to explicitly, prognostically model the vertical motion, and then whatever convergence I have in the horizontal, that'll give me my vertical motion, right? But look, this vertical arrow must now compensate for the gross convergence from the blue arrows. There's no offset here, right? And so that tells you that hydrostatic vertical accelerations are always going to be greater than non-hydrostatic vertical accelerations. So you can also kind of try to capture this analytically. And so what I did was I considered a density distribution that was a little bit different than the ones that I showed you, but still highly idealized. And idealized enough that I could derive analytical expressions for both the non-hydrostatic beta over B naught and the hydrostatic beta over B naught. So I got these nice simple formula, and I can plot these. This is what they look like. And so you see that, yes, in the hydrostatic limit, both accelerations go to 0, and the accelerations agree, right? They go to 0 in the same way. And in fact, you can just Taylor expand this expression in the limit of very large d over h, or very small h over d, and it agrees exactly with this expression, as they should, right? That's that's what the hydrostatic approximation is built on, right? Okay, so everything is as it should be out here. But the point is that as you sort of go into the gray zone, your non-hydrostatic accelerations converge to the Archimedean value, but your hydrostatic accelerations diverge out to infinity. So if you're running a hydrostatic model and you're ramping up the resolution, your accelerations are going to start to diverge. So your model might start to look pretty good around here because your ratio of effective to Archimedean buoyancy is 1, but you're sort of, in some sense, you're getting the right answer for the wrong reason. And if you kept pushing the resolution, your results would diverge. And so one of the things I plan to do at GFDL is that they have a dynamical core that contains a switch that allows you to flip from hydrostatic to non-hydrostatic. And so I want to run simulations in both hydrostatic and non-hydrostatic mode and basically make the same plot. Oops, I think this thing is cached out. Basically make the same plot but using simulation data rather than analytical formula, and show that the analytical formula, at very least qualitatively capture what the simulations are going to do. All right. So to summarize and kind of give the take-home messages, I guess maybe the first take-home message is that the actual vertical acceleration that a parcel experiences, or the actual thermodynamic acceleration that a parcel experiences, which is the effective buoyancy, can be very different from the Archimedean buoyancy. And you can actually describe this difference analytically using this formula, and you can understand them using this buoyancy pressure that we've introduced. And with these tools in hand, you can actually then understand what triggers convection, why Archimedean buoyancy is so different than effective buoyancy, and then use these analytical formula sort of to describe what's happening in idealized cases. So there's many applications to convective dynamics, both in sort of a comprehensive and idealized setting. And that's all I have. Thanks.
All right, so we have time for some additional questions.
Yeah.
When I look at the high resolution simulations of deep convection, like ITPA and LAS, I always see that there are no big parcels. Like even for big clouds, you have just basically many parcels merging together, coexisting like very in close proximity. So convection somehow does apply this regime of pancake.
That's right.
You described. So this only true for low resolution models, and this is what you will see. Like when I run at this 4-kilometer grid spacing, I see my acceleration is barely moving.
Yeah, that's right.
But
That's right.
It's quite but actual convection never moves in big parcels. So do you understand why it cannot actually create this small scale features instead of going as a big bubble?
Right.
What's the advantage of that?
What's the what?
What's the advantage for clouds?
Well, I mean, maybe one way to answer that question is just to say that if you have, so maybe in some sense these plumes are unstable, right? In that if your plume is very wide, right? So let's say it's rising like this uniformly, but there's going to be some perturbation. So let's say one side starts to rise up a little bit faster than the other, right? Then all of a sudden, the aspect ratio of this part of the plume is, maybe half that of the larger plume, and that's going to kind of move you up here, and maybe that creates an instability, right? So now, if these are just two halves of my plume and this one moves up a little higher, then this one is accelerated even more, and then you kind of have some separation. So I can imagine that that's something that might happen, say, in the boundary layer where plumes are generated, right? Is that they have a tendency to split basically because of the shape of this curve.
What determines the size of this optimal?
That's a great question. I don't think we have an answer. Some people postulate that, people have noticed that the depth of the boundary layer, 500 meters to 1 kilometer, and sort of typical.
Yeah, but it can be coincidental.
I mean, no one has established, a definitive link. But I think a lot of people do think that the depth of the boundary layer is what sets the width of convective parcels. But we don't know for sure yet.
Yeah, I'm thinking about a question about the time scale for this process. Basically, we have the convection, we have convective equilibrium. In the meantime, we have the cold surface. Okay, these three processes.
Sorry, in the meantime, you have what?
Well, convection, radiative convection equilibrium. Second one, third one, cold surface.
Cold surface. You're talking about the cold pools?
Yeah, cold pool.
Yes. Uh-huh.
Well, cold pools, if we're supposing that comes from the ocean surface.
Sorry, do cold pools do what?
From ocean surface or water surface or some kind of surface. What is surface?
What is the surface in these simulations?
Yes.
Oh, yeah, it's an ocean surface.
Ocean, okay.
Yeah.
Humanity, okay. To cool down the ocean surface take a long time. Person.
Oh, you're asking what are the impacts on the ocean?
Yes.
I see.
Well, this is the third one. Longest time scale from the ocean surface. Shortest scale is the convection cell.
Uh-huh.
Then radiative, we need at least a Downers cycle.
Uh-huh, okay.
So there's three different time scales for these three different processes.
I see, uh-huh,
So
yes.
I'm trying to understand how to bring them together to make this model work.
Oh,
So maybe quickly, for your simulations you showed earlier of the cold pools, I mean, those are prescribed.
yes, it's a fixed SST.
And there's no diurnal cycle.
There's no
And
correct. There's no diurnal cycle. I mean, there is radiative cooling, and it does have a time scale, right? I mean, radiative adjustments do take several days. But yes, maybe I should have been more explicit about this. But the ocean surface is it's a fixed SST. It's not a slab ocean. So when it gives up heat and moisture, it doesn't change the ocean surface at all. So the ocean temperature does not respond to the surface fluxes.
Does that mean the cool pool is actually the atmospheric cool pool?
Yes, it's the atmosphere. Correct. It's not a cold pool of water. It's a cold pool of air.
So okay, that'd be even more interesting now because we fix the ocean surface, we're cooling down the surface layer right above the ocean.
Correct.
Surface.
Yes.
It's definitely going to enhance substantially sensible heat flow.
Absolutely. Yes. And the latent heat fluxes. And in fact, the reason that there's this thermodynamic enhancement at the edge of the cold pool is because that cold pool, as it slumps down and spreads out, it has significant horizontal velocities, so that increases the flux off the ocean surface. And so you have the edges of the cold pool tend to be anomalously warm and really anomalously moist because they've picked up a lot of fluxes. So you can certainly see the signature of the cold pools in the surface fluxes. Absolutely. Yeah.
So, do you have explanation, like when you run the simulations, you claim that it starts from cold pool edges. If you look at moist, you see this moist static energy actually enhancing.
Yes.
So why moist static energy is enhancing?
It's mostly from the moisture, and if you look at the sort of the circulation in a cold pool, there's basically the cold pool slumping down and spreading out, but there's kind of this vortical circulation at the edge of the cold pool, and that's actually if the edge of the cold pool is doing this, it's kind of scooping up that low-level air into the vortex. So the vertical velocities here are actually extra high. The vertical velocity is here, so if the gust front's here, the vortex is here, it's propagating this way, the center is here. This horizontal velocity is actually much greater, or it can be significantly greater than the gust front velocity. And so this air, which is the air that's picking up all the surface fluxes, is actually then just kind of getting folded in to the gust front. And so all this extra moisture that's getting picked up from this propagation outwards is all getting concentrated in the gust front. And that's why you see the anomalous moisture there. And it's that anomalous moisture that drives the high moist static energy.
How concentration is incompressible?
Sorry?
It's incompressible system.
Yeah.
So how do you compress something?
No, it's not compressed. I mean, there's entrainment. So I mean,
You should. That's what you showed. It's actually vertical integral, right?
no, I was showing single model levels when I was showing.
Single way.
Yeah.
Then I don't quite understand how.
Oh, I see.
Because a continuity equation is how you actually increase the weight.
Well, I guess what I would say is that the QV, or the specific humidity of, again, if the gust front's here, and then there's very low-level air being drawn in, then what must happen is that the specific humidity of that air is extremely high, right? And then as it gets folded in, it's sort of, there must be some mixing, right, and dilution.
So let's say that it's completely uniform in boundary layer, water vapor. Then you have cold
No, but when you look at a cold pool, it doesn't look uniform.
No, I mean outside the cold pool.
Oh, yes.
And then you have cold pool propagating. How locally you can increase it? Continuity to allow.
How does the water vapor?
Local continuity, well, basically, advection equation says that along the lines, water vapor should be constant along the trajectory.
Maybe another way to think about it is that you are getting enhanced vapor fluxes off the surface, and those have to go somewhere, right? You have the velocities are higher than they are typically, so you're getting more flux off the surface. It's got to go somewhere, and where it ends up is in the gust front. I'd have to think a little bit harder about exactly how the advection works, but I think just from a conservation point of view, more fluxes got to go somewhere. The gust front is where it ends up.
In terms of the equation, you mentioned the thermodynamic term and the dynamic term.
Yes. You're talking about the force decomposition.
Okay, so because I'm not good at the mesoscale equations, so can you explain more about the thermodynamic term? What's the difference between this term with the pressure and radiation term in the Buoyancy equation? And secondly, what is the typical time scale of these two terms?
Well, the answer to the first question is that, and this goes back to a question that Murat asked. So you can show mathematically, Davies-Jones did this in 2003, that if you take the Archimedean buoyancy plus the perturbation pressure gradient, and you add those together, it's the same as the effective buoyancy. So it's just an alternate description.
So does the sound wave also filtered in the equation, right?
The sound wave is filtered in this framework.
Means of the density, right?
Sorry?
Because you use the mean of the density.
That's right. Yeah, you can think of this as a kind of anelastic framework where I'm using a reference profile of density, and sound waves are filtered out.
So how about the time scales of these two terms?
You mean what's the time scale of the effect of basically of the environmental response to the so in this context it's instantaneous because that would happen the mass continuity, right, propagates at the sound speed, and so what's happening in the anelastic framework is that you're assuming that happens instantaneously, and that's why you're able to diagnose this environmental pressure that's responding to the Archimedean buoyancy, right? The perturbation pressure is responding to the Archimedean buoyancy, and so the time scale it's instantaneous. Because in reality, it would happen on the sound speed scale, but here we're approximating that as instant. Does that answer your question? Okay.
Welcome. This is an oceanographic question. Every January in the Gulf of Leon, which is the northwest Mediterranean Sea, the cold, dry winds, the Mistral, the French Alps, I think, blow over the Mediterranean, cause a lot of cooling, and you get these very well-defined and relatively narrow, I can't remember maybe the size of this room, sinking plumes, which sink down to 1,000 meters of water to the bottom.
Oh, wow.
And the vertical velocity is a meter per second or more, which for the ocean is huge.
Yes, right.
So I'm just wondering whether some of your ideas might apply to those kind of presumably incompressible dynamics.
Yeah, I mean, I guess the question would be, do you think the aspect ratios of those plumes are much different from the aspect ratios of other convecting plumes elsewhere in the ocean that move slower?
Yeah. I don't expect to know the answer.
Yeah, I mean, I would expect that. I mean, this is sort of like the 0th order physics of how these motions take place. You know, so I would expect that. So I guess the question is, you know, how are those vertical velocities so large relative to other vertical velocities observed in the ocean? And I mean, you know, my guess or my conclusion from this would be that it either has to be, I mean, was it a factor, an order of magnitude larger, those vertical velocities?
Well, I don't
Maybe-
know about,
maybe two?
Maybe Chris can speak more to that. About radial overturning. What kind of sinking velocity are you talking about?
I think we're talking 10 centimeters per second, which is vastly larger than the average
Right.
vertical velocity, which would be micrometers per second.
Right.
or
Right.
maybe
Okay.
millimeters per
So maybe these plumes are an order of magnitude